In this video, we're going to take a look at power functions. Power functions are functions that are of the form x to the n, where n is a positive integer. This fancy symbol z means it's an integer with a little plus sign that says we're talking positive integers. So 1, 2, 3, 4, etc., etc. Okay. Now, we already know the rule if n happens to be 1. If I want to take the derivative of just x, which would be x to the first, the function y equals x is just a linear function. That's a line of slope 1, and the derivative of a line is just the slope of that line. Okay. So what we're going to do in this video is we're going to work it out if n is bigger than or equal to 2. So we're looking at things like x squared, x cubed, etc., etc. Okay. Now we'll see that the rule that we get will actually work if n is 1 as well. But this is the new stuff that we don't yet know. Okay. So I'm going to just draw myself a picture of a power function. Now power functions, if they're even, the graph looks kind of like x squared. It looks like a parabola. And if they're odd, the graph looks something like x cubed. I just made a choice. I happen to have drawn the graph of an odd power function, but the algebra that we're going to do is just going to take advantage of the fact that my function is f of x equals x to the n, where n is a positive integer that's 2 or bigger. Again, the definition of a power function includes the linear function y equals x to the first, but we already know that derivative. All right, so if I have a point x, then the y value is x to the n. And if I choose a nearby point, x plus h, the y value is what I get when I replace my input with x plus h. So I'm going to be taking x plus h to the nth power. There's my secant line, and I know that f prime of x is the limit as h goes to 0, rise over run. So x plus h to the nth minus x to the nth all over the run is just h. And so now I need to expand out this power of x plus h. Now I know that what that means is that I've just got n factors of x plus h. So if n is 2, I've got x plus h times x plus h, and I just FOIL that out. But I'm trying to do infinitely many problems at once here. I don't want to have to evaluate one limit to see what the derivative of x squared is, and another limit for x cubed, and another one for x to the fourth. I'm trying to get a rule for any power. If I don't know how many factors of x plus h I have, it's going to be difficult to multiply them all out. And it would be really tedious if n was big, even if I did know how many factors I had. But there's a nice way that we can get around that. I can observe that that's a binomial. It's a sum of just 2 terms. And so I know how to evaluate a binomial to a positive integer power. The binomial theorem tells me how to do that. Now, this is an optional topic in our pre-calculus class. So depending on where you took pre-calculus and with whom you took it, you may or may not have seen this in your pre-calculus class. My guess is you saw it at some point in some sort of an algebra class, but I'm going to basically just tell you what it says. It tells me that when I multiply out n factors of x plus h, the types of terms I get are all going to involve n factors of either x plus h. So I'm going to get some terms where I just have n factors of x. But I'm going to also get some terms where I have one less x, but I have an h. So I still have n factors, all of which are either x's or h's, but just some of them are x's and some of them are h's. And I'm going to have every possible combination of that. So if I have one less x, I'm going to have one more h. So I would have, if I have n minus 2 copies of x, I would have 2 factors of h. So that the exponents always add up to n. Here I've got n x's and 0 h's. N plus 0 is n. Here I've got n minus 1 x's. I could write h as h to the first. N minus 1 plus 1 is n. And we just keep going all the way down. So I would have some copies of just x and then h to the n minus 1 plus some copies of h to the n. Okay. All right, so I got a little bit squished there, but those are the types of terms that I have. Now, I've left these blanks here for the coefficients. For the coefficients, we can get those using Pascal's triangle. Let me erase the graph here because we've used that already. Pascal's triangle looks like this. The first row is 1 and 1. Those are the coefficients that show up in the first power of x plus h, because x plus h to the first is 1x plus 1h. Okay. To form a triangle, we go diagonally out, left and right, and then we have to fill in this middle ground. And the way we do that is there's a space here that has 2 numbers above it, and we just add those. 1 plus 1 is 2. And we know if we FOIL out x plus h squared, we will get 1 copy of x squared, 2 copies of xh, and 1 copy of h squared. So these are the coefficients that we get for the second power of x plus h. Then we come on down. We had a problem in the last section where we had x plus h cubed, and we actually used the binomial theorem to evaluate that. 1 plus 2 is 3. 2 plus 1 is 3. The coefficients for x plus h to the third are 1, 3, 3, and 1. X plus h cubed is 1 copy of x cubed, 3 copies of x squared h, 3 copies of xh squared, and 1 copy of h cubed. Okay. Now, you might say, how does this help us? Because if we don't know what n is, we don't know how far we have to go. All right, but it still does help us, okay? Because here's what I'm going to do. I'm going to say that this is the limit as h goes to 0, and I can see the pattern for the first couple of terms. We always start with a 1. So whatever n is, I'm going to have x to the n, and I'm going to have 1 copy of x to the n. Then the next term, notice the next term is 1, then 2, then 3. I can see it's going to become 4. And then I'd have for the next one 1 plus 4. The next coefficient is always just n. Okay. So I'm going to have n copies of x to the n minus 1 times h. Okay. Plus a whole bunch of other terms. But what those terms are going to have in common is that they're going to have at least 2 factors of h in them. So I'm just going to write that as terms with at least 2 factors of h. Now here's why I said that we're using this derivation here if n is at least 2. If n is at least 2, then I'm at least in this row where we've got x squared, 2xh, h squared. We do in fact have 2 h's. Here this would be x cubed, x squared h, xh squared. We've got at least 2 h's, and then h cubed. Okay. So if n is at least 2, I have at least 3 terms. The first 2 look like this, and all the remaining terms have at least 2 factors of h in them. Okay. So that's my x plus h to the n. Now don't forget, we've still got to subtract x to the n and then divide by h. So what we've done here is we've used the binomial theorem to just expand that power, x plus h to the nth. Okay, this is looking good. Because now the only term that doesn't have an h in it, is x to the n and minus x to the n, and that's going to cancel. Now when that cancels, every term that's left on top has at least one h in it. That has exactly one h, and all of these guys have at least two factors of h. So I'm going to do what I usually do. I'm going to factor out an h. Now when I do that, from this term I pulled out the one and only h. What's left is n times x to the n minus 1 plus, now here these guys had at least two factors of h. If I factor one of them out, I've got terms with at least one factor of h. And then this is all over h. I can cancel that h. And so now we've got the limit as h goes to 0 of n times x to the n minus 1 plus terms with at least one factor of h. But now I don't have that h in the denominator. I can plug in h for 0. So I'm going to get n, x to the n minus 1. And all of these terms that have at least one factor of h in them just become 0. And so I get n, x to the n minus 1. Very cool. That's what we call the power rule. Let me just write that down here. Power rule says the derivative of x to the n is n copies of x to the n minus 1. So, we've seen before the derivative of x squared. Notice that's a power function. So I can say, okay, I take that power, I bring it down and it becomes a coefficient. And then I multiply that by x to the 1 less power. But 1 less than 2 is just 1. That's 2x. That's a result we've seen before. The derivative of x squared is just 2x. Now here's one we haven't seen before. The derivative of x to the 45th. Now, I might not want to have to work this one out, but I don't have to, because I can use my power rule. I can say that power comes down and becomes the coefficient, and then I multiply that by x to the 1 less power. 45 minus 1 is 44. So I've got 45 copies of x to the 44th. All right, now the derivation that we did proved that this worked if n was 2 or bigger. Notice, if I were taking the derivative of x, which is just x to the first, okay, the power rule here does work as well. I would say that 1 comes down and becomes a coefficient, and I'm multiplying by x to the 1 less power. But that would be x to the 0. And remember, anything to the 0 is just 1, and so we get 1. So although the derivation that used the binomial theorem doesn't work in this case, because we won't get any terms that have at least 2 factors of h, which we relied on there, we worked out separately that the derivative of a line was its slope, but that's consistent with the fact that x, which is a line of slope 1, is also a power function, and the power rule does work in that case as well.